Applications of differentiation. Applying delta y is dy dx delta x, that's the small change formula, to differential equations. The idea is quite straightforward. Suppose we know that dy dx is a function of x and y, so it will be an actual function that we have. So we have dy dx is a function of x and y, and we have a start point here, p0, x0, y0. That's a point that we know is on the integral curve of this equation. We can compute the value of dy dx at p0, x0, y0 by substituting in the x coordinate and the y coordinate to this formula. We decide on a value for delta x, so that's under our control. We can choose delta x to be any step length that we want. Then we compute delta y1 by using delta y1 is the value of dy dx at x0, y0, this point here, multiplied by delta x. So we're using the small change formula there. Then x1 is going to be x0 plus delta x. y1 is going to be y0 plus delta y1. So we've taken a step from p0 to p1. So on the diagram, the x value steps up by delta x, the y value will step up by delta y1, taking us to this second point, which we're estimating is on the integral curve, and then we join them with a straight line, but that straight line is there to approximate the integral curve between these 2 points. Now I should clarify what I just said. The only point that we actually know is actually on the integral curve for the differential equation is the point that we're given. But this next point is an estimate of the value of y1 at x1 on the actual integral curve. So we can repeat the process by then computing that delta y2 is dy dx evaluated at our new point multiplied by delta x. Then we do the same sort of calculation as before. x2 is x1 plus delta x, y2 is y1 plus delta y2, and then we take a further step. So we go delta x across again. The new computation of the change in the y coordinate, delta y2, is here. That takes us to this next point, and we join them to give us an estimate of the integral curve along here. By repeating this process, we can build up a picture of an integral curve for a differential equation, even if we cannot solve the differential equation. There are some issues, however. The method works best if delta x is very small. We get better approximations if we don't go too far. Remember, the only point we were actually certain about is the point we're given at the beginning, the x0, y0. After that, every point is an estimate of where the integral curve goes. Asymptotes or other discontinuities cause problems. Clearly this method is related to the section on tangent fields. We're using a tangent field that's very, very fine to use this method.